Okay, hey, what's up, folks? I just want to finish off the last little part of this lecture, so I'm just going to try to do this kind of quick instead of fooling around. So this is going to be one of our first kind of hardcore derivations. So I want you to pay attention and follow through how we apply, in this case, the molecular partition function and expand it into what we call the Maxwell-Boltzmann distribution. Okay, so here we go. So if you recall, the molecular partition function looks like this. So Q is the sum, and if degenerate or equivalent energy states exist, there's this degeneracy factor, right? As well as, this E raised to the power negative energy sub I corresponding to whatever state is in that sum divided by K Boltzmann T. Okay, so now we're going to expand this specifically for the translations of molecules and their kinetic energy. Okay, so I've used the letter I here, but note that that's just generic, right? So that letter is going to change. So for example, we know that kinetic energy, EK, of an object can be written as 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. So already we can kind of start to see what this whole degeneracy thing is going to give us, because motion in the x, y, or z should be degenerate for a gas. So we're going to have to take advantage of this degeneracy term. Okay, and so now I'm going to write out, using a little bit different notation, a new function here that we're going to develop. And that function is going to go as the following. I'm going to use a capital K in place of this letter G. And I'm going to write e to the negative e k divided by K Boltzmann T, where we recognize this now EK is my kinetic energy. And I'm going to go ahead and expand that. And here I'm going to use my EXP notation because this exponential is going to get a little hairy. Okay. And so that I'm going to write as, let's see, negative. I'm going to put a big parenthesis around 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared, and of course all divided by K Boltzmann T, right? So note all of that is in the exponent. And now I can take advantage of a trick, an algebraic trick with exponents. So I'm going to separate those out, okay? And rewrite my function as K exp, oh, let's write K times all this stuff, okay? And that's going to be, let's see here, negative mvx squared divided by 2 kbt times exponential of negative mvy squared divided by 2 kbt times then the exponential of negative mvz squared divided by 2 kbt. Okay, and so now we can start to see that we're going to have a way of separating those degenerate states, those x, y, z states. Okay, and we'll also put some language of calculus in here so that we can use calculus. So I'll say if f of dvx, dvy, dvz is the fraction of molecules, is fraction of molecules in the range, Vx tends to Vx plus dvx, right? And Vy tends to Vy plus dVy, and then we can say the same thing about Z, okay? Vz tends to Vz plus dVz. Okay, so this is just allowing us to use the language of calculus. And so thus I can now write a function f of v total, which is going to be some product of these individual functions. All right, and then of course, that's all. So there's a times dv and times dv, right, on both sides. Okay. So for example, I can now talk about this just in terms of the z dimension by saying, for example, f of vx dvx equals, now I'm going to write this as exp negative mvx squared over 2kbt dvx. And now what about this k term? Well, because it's degenerate, we know it's going to apply evenly throughout each of those dimensions. So I'm going to write k to the 1/3 power. And so when it gets recombined into all of these individual functions, I'll get back to the original function that I had. I'm also going to note that I can say the integral from negative infinity to infinity of this function f of vx dvx integrated right from negative infinity to infinity will equal 1. And all that's saying is from negative infinity to infinity, there's 100% chance that we'll find that particle somewhere. Okay, so that's what this means. So what we've done is normalized this function to 1. And what that also allows me to do is determine the value of this constant k. So I can treat this as a normalization constant. So for example, doing some algebra, I can now say 1 equals k to the 1/3 power, because it's a constant. I'm taking it out from the integral sign. Okay, I don't need to put that in the integrand because it's a constant. And now that's going to be, replace this with f vx dvx, right, this function here. So that's going to be my exponential function of negative mvx squared to kbt times dvx. All right, fantastic. Okay, and from here, right, I know we're learning how to use Mathematica, so we could plug this into Mathematica and it could solve that function for us all day. However, I'm a huge fan of integral tables. And as it turns out, there's a standard solution for this integral, and it goes as the following, okay? When you have an integral from negative infinity to infinity of exponential negative ax squared dx, and if you compare this to this, right, they're the same. My a is m divided by 2kbt, right? Okay. Then this has a very simple form, and so the solution to this integral is pi over the constant a to the 1/2, so the square root. So now we can very simply solve this integral by just substituting what we have for a, and I'll go ahead and do that on the next slide, okay? So keep that in mind. So I'm just going to write the solution of this. So here we recognize a is m divided by 2kbt. So our solution will be pi divided by m divided by 2kbt, and we'll do the algebra to make that look a little bit nicer. Okay, so now that's going to go 1 equals k to the 1/3 power. And here I'm just going to write that integral solution with the algebra already done, 2 pi kbt divided by m all to the 1/2 power square root. So stop and make sure that you can do that algebra from the previous slide. Okay? And so from here we can solve for that constant k. And I'm going to just do the algebra very quickly. So that's just k equals m divided by 2 pi kbt all to the 3/2 power. And I want you to note here, I'm going to give a few options. When we use a lowercase m in this class, this is very subtle. Actually, here, let me do this. Let's change colors. Yeah, let's be all slick and cool. So when I use a lowercase m, okay, that corresponds to kilogram per molecule, and thus you have to use K Boltzmann. Okay? But if I use a big capital M, that corresponds to kilograms per mole, and you may have guessed it, we'll use Batman, the gas constant, right? So I'll say that's now or big capital M divided by 2 pi RT to the 3/2. So either of those are okay. It just depends what constant you're going to use. So pay attention to that in this class. That lowercase m is specifically kilogram per molecule. The uppercase m is kilogram per mole. And of course, this would give us the molar mass in terms of kilograms. Okay? So now I can go back here and I can write my function f of Vx equals that constant k raised to the 1/3 power. I'm going to go to using r, that's a capital M, 2 pi RT. Now to the 1/2 power, okay, and then that's times the exponential of negative m, capital M, right? Negative m Vx squared divided by 2 RT. And so that's going to be our function for f of Vx. And of course, we can combine this now for everything. And so when I do that, I'm going to write this as f of V now. And I recognize that this constant is going to get cubed because it's got 1/3 contributions to each dimension. So now that's going to be capital M divided by 2 pi RT to the 3/2 power, all times the exponential of, let's see here, that's going to be negative capital M, just V, for Vx, Vy, Vz, squared over 2RT. And of course, if I multiply this by my volume element, dVx, dVy, dVz, then I do the same on this side, dVx, dVy, dVz. Okay? And I also recognize that in my volume element here, right, if I take the integrand from negative infinity to infinity of that volume element, dVx, dVy, should be a z. Okay. This equals the integrand of 4 pi v squared dv. And of course, if we then go and finish off that integrand, right, you get 4/3 pi v cubed, which is our volume of a sphere, right? And of course, I'm using v for velocity, but if we would replace that with r for radius, right, this is the volume element, 4 pi r cubed, all right? So now if I apply that through to my function here, I can finally write, so let's see, do I have another slide? Oops, okay. I can finally write f of v equals, and I'm just going to keep it as this integrand, right? Because you notice here that I've got to integrate this side, and I've got to integrate this side. So I'm not going to have the contribution 4/3 pi v cubed. I'm going to have this contribution right here because I have the integral of each side. All right. And so finally, that's going to go as 4 pi that I get from right there. Okay. And then I have this constant, capital M, 2 pi RT to the 3/2 times v squared, okay, and then times the exponential of negative capital M v squared to RT. Yes. And this equation is our Maxwell-Boltzmann distribution of velocities, okay? And we're going to play with this equation a lot in the coming weeks in your Mathematica slides, okay? And so there's a few things that I want to point out here. Let's see, I think I ran out of slides, so I'm just going to start this fresh new slide, okay? So if I give you just kind of a general, start to give you a general plot of what this Maxwell-Boltzmann distribution looks like. So if I plot v on this axis and f of v, so velocity and the fraction of molecules with that velocity, then I get a very famous looking, I get a famous looking curve called the Maxwell-Boltzmann distribution. Man, there's not supposed to be a little thingy there. It's supposed to be a nice smooth function. It appears as if it should be like a Gaussian distribution, but it's not. It's not Gaussian. It is weighted heavy at the tail end. And so if I said, like, for example, this is the distribution at T1, and I think I need to make some more room here. And I'm also going to define, I'm going to say T1 is less than T2 is less than T3. And if I look at these three different temperatures, right, then these are the distributions that I get. So T2 would look something like this, and T3 would look something like this. And what I want you to take note of, the maximum of these curves goes out to larger and larger velocities. So this is consistent with what you learned in general chemistry with respect to gases. The higher the temperature of the gas, the faster it moves, and the more chaotic it is. So as the temperatures get bigger, this distribution spreads out. As it turns out, if you integrated the area under all three of these curves, they would all give you the same area because we're talking about the same relative population of molecules. However, for a higher temperature, the population of those states will be spread out. So there'll be a much larger range of velocities for a larger temperature, which is consistent with our postulates of the equal partition theorem. Okay? And so the last thing that I want to talk about here is some calculus analysis on these distributions. And I'll just go and draw one representative distribution here. So as I said, it's not quite a Gaussian. It's kind of, it's weighted towards the heavier side, okay? So here, this area that I'm calling, that's the most probable speed, which I'll call C star. Out right here, I'll give this big, long, dashed lines. So let me write that down. So that's most probable is the peak, okay? Then out here is actually the mean, the arithmetic mean given by C bar. So because this is an uneven distribution, if we took the area under these curves, the area on the left side of the mean would be the same as the area on the right side of the mean. But it's going to be a different velocity than the most probable velocity because it's not a symmetrical distribution. And then finally, out here to an even higher velocity would be called the RMS, which is the root mean square. And we'll spend a lot of time talking about RMS, root mean square. Okay? And so I'm going to back up one slide here. And so here I have all these different velocities, most probable speed. So again, I'll write that as C star. The RMS is just C, and the mean speed is C bar. So I'm going to write how to find these using calculus, but I'm not going to finish off the solutions. The solutions are in my Fall 19 notes, which are posted, but you should definitely try to see if you can knock off the dust of your calculus and figure these things out. Okay, so most probable speed, if we go back and look at this for a second, so the most probable speed is at the very top of this peak. So think about that for a minute. How would you do that? Okay, you would do that with the following. F prime of v set equal to 0, right? You take the first derivative of that function and set it equal to 0. And the result that you should get, you should give this a try. C star will equal 2 RT divided by big capital M all square root. So see if you can get that. And the hint that I'll give you a hint on this most probable speed. dx of e to the power u equals e to the power u times du dx, right? So when you're taking the derivative of a function with an exponential, you just keep the e to the u, but then times the derivative of what's inside the exponential, right? Du dx, okay? So see if you can arrive at this solution. So the mean speed, I'm going to write out over here. I'm going to start it over here for the mean. Okay. So I'll also give that another symbol, bracket v bracket. So that's another way of writing the mean. And we can always find an arithmetic mean through integration by saying from 0 to infinity of v times f of v times dv. This is actually the formula for determining a mean when you have an area under the curve. Okay. And let's see, the solution for that one, did I write it down? Let's see, the mean speed. So the mean speed you should get for this one, C bar, is 8 RT divided by pi times big capital M square root. So see if you can arrive at this result. And the hint that I'll give you for doing this one is one of these integral solutions, which is when you take the integral from 0 to infinity of x cubed times e to the negative ax squared dx equals 1 over 2a squared. So that's your hint for trying to solve that integral. And then finally, the root mean square speed is exactly that. It's the root of the mean squared. Okay? So I can write that as the following. Okay? So brackets mean mean. The brackets mean the mean, the arithmetic mean, okay, squared, and the root. So the root mean squared. Okay? And so that equals C, which equals very similarly to the mean that I wrote here. So integral of, we can integrate that from 0 to infinity since we don't have any, anything in the negative velocity ranges. Okay? So we wouldn't get any benefit from integrating to negative infinity. Okay, so then now that's going to be v squared f of v dv square root, and then let's see here, all, so all this is in brackets. So then you take that final result, all square root. Okay, and so your hint for, I'll give you the solution for the RMS speed. You should get 3 RT divided by M, all square root. Okay, and then your hint for this one is for RMS, another one of these integral table solutions, 0 to infinity, x to the 4th, e to the negative ax squared dx, and this has a standard solution which equals 3/8 pi over a to the 5th power all square root. So see if you can do these. See if you can knock off some of that dust from your calculus days. I have the solutions available in the notes, but I think this will be some good practice for you. Okay, so that covers it for week 1. Starting next week, we're going to get into thermodynamics. We will actually start with chapter 1. Okay, and I'm not going to go over the learning goals here in this video, but in the module 1 on Canvas, download the learning goals sheet and make sure that you're making good progress through those. And I'm going to talk more about those learning goals during our live meeting on Friday. Okay, folks, I will see you then.